Okay, good afternoon, folks. Today we're going to finish off min-cost flow and move on to our even bigger generalization of linear programming. Logistical point, I'm not going to be here on Monday, but there will be no recorded lecture because you also won't be here on Monday because it's vacation. So enjoy your Monday off. But we'll still be able to get started on linear programming today, and then I'll see you again on Wednesday. So last time, while I was away, we introduced this notion of feasible price functions. Right? We said that if the min-cost circulation of a network is 0, that holds if and only if there exists feasible prices. Right? This is because feasible prices essentially surface and prove that there are no negative cycles in the network. Right? There may be negative edges in the network, but when you create feasible prices, it moves the costs around. It moves that so that negativity is all canceled out by positivity in other parts of the network, and you're left with a network that has no negative cost arcs. And of course, if there are no negative cost arcs, then there are obviously no negative cost cycles. However, the price function didn't change the cost of the cycles because it telescopes. It cancels the cost changes cancel around a cycle. And so the cycle costs are the same as they were in the original network, but now they are transparently all non-negative. And that tells you that the min-cost circulation is optimal. And we also know that a flow is a min-cost flow. Gee, what's going on with this chalk? A flow is a min-cost flow if and only if the residual circulation, the min-cost circulation in the residual graph is 0. So again, the way that you can tell that you have a min-cost flow is by providing feasible prices on the residual graph, right? Which make all of the residual arcs have non-negative costs. Okay? And we use this idea to develop another approach to computing min-cost circulations and min-cost flows. In particular, we showed that if all of the edge costs are non-negative, then computing a shortest augmenting path and saturating it does not, actually, I didn't need this caveat. So let's try again. If there are no negative cycles to confuse things, then computing a shortest augmenting path and saturating it doesn't create negative cycles. Right? Now, I mean, if there is a shortest augmenting path, then saturating it doesn't create any negative cycles. The issue with having negative cycles is that if you have negative cycles, there isn't a shortest path because you can go around that cycle and it can get infinitely short. So the algorithms that we started talking about last time were algorithms that we sort of started with an assumption that there were no negative cycles, and we preserved that assumption. So for example, right, if you have a graph with no negative arcs, then what you could do is compute a shortest augmenting path, which does not create any negative cycles, right? And you saturate that that shortest augmenting path. That doesn't create any negative cycles, and so now you can compute feasible prices in the new residual graph. And that means that, again, you have no negative edges because your feasible prices do away with any negative edges, right? If this is completely unfamiliar to you because I'm wrong about what you covered in the recorded lecture, you should ask me questions. But hopefully this is just a recap of what you saw in the recorded lecture. Yes? OK. And how do we compute feasible prices in a network with no negative cost arcs? Or in general, actually. If there is a feasible price function, how can we compute it? Yes? Shortest paths, right? So any shortest path algorithm the distances that you get out of that shortest path algorithm are feasible prices, right? And if you have no negative edges, you can, of course, use Dijkstra's algorithm to compute those distances. So this whole process of computing the shortest augmenting path and then augmenting along it and ending up with, again, no negative cost edges, that's going to take order m time per shortest augmenting path computation, right? Or order m log n. Right? And so this gives us a polynomial time min-cost flow algorithm in the unit capacity case. And this is where we kind of finished up last time. Right? In a graph where all of the edges have, or sorry, let's say integer capacity network. Right? In a graph with integer capacities, okay. Maybe I'm a little too excited about min-cost flows. In a graph with integer capacities, you need to do f shortest augmenting paths for a flow value of f. And that means that your overall runtime is going to be mf log m to find a min-cost flow. Right? Now, we also, on Monday, drew this connection that says that you can also use a min-cost flow algorithm to solve min-cost circulation problems and vice versa, right? And I gave some reductions for doing that. But we're going to look at a somewhat different reduction, different reduction now. Sorry, we're going to now start thinking about what if you have negative edges. Right? So we want to solve a min-cost circulation problem. We have negative arcs. We have this nice algorithm that solves min-cost flow problems when there are no negative arcs. How can we apply those ideas to doing a min-cost circulation problem where there might be negative arcs? The answer is that we start by saturating all the negative arcs. And that just sort of creates excesses and deficits at various vertices. Okay. So what do we need to do? We use a min-cost flow algorithm to send the excess to the deficits. right? And so implicitly here, we're solving a sort of a generalization of the max flow problem where you have many sources, each of which has a fixed amount of excess, and many sinks, each of which has a fixed amount of deficit. And we're asking for a flow that delivers all of that excess to all of that deficit. But this is easy to see as a simple generalization of the standard max flow or min cost flow problem. You just take all of your excess vertices on one side and your deficit vertices on the other side. And you create a super source with the appropriate excess amounts of capacity to each of the excess vertices, and a super sink with the appropriate amounts of capacity on the deficit edges, right? And now you just compute a max flow from the super source to the super sink, and assuming the problem is solvable, that means there is a solution that that saturates all of the source edges and all of the sink edges, and so that will send the appropriate amount of excess to the appropriate amounts of deficit. Yes? Yes? This was on our homework, right? Yes, or it's part of. Part of. Okay. Yeah. See, it's good to go to lecture. You sometimes get a little freebie stuff. Yes. So now that we have this, we can use this technique to reduce a min-cost circulation problem that has negative arcs to a min-cost flow problem without negative arcs, right? And so we know how to solve that min-cost flow problem without the negative, once we've gotten rid of the negative arcs. Now what if we want to do a min-cost flow? With negative arcs. How do we solve that problem? Yeah.
We showed earlier that you can reduce min-cost flow to min-cost circulation.
Right.
And then you can reduce that again to min-cost flow without.
Exactly. Right. So we're going back and forth between min-cost flow and min-cost circulation. Right. So what we showed on Monday is that you can find any flow, just ignoring any max flow, just ignoring the costs, and then you can find a min-cost circulation in the residual graph. Right? And because the max flow that we found was not a min-cost flow, there might be negative cost arcs in the residual graph, but that's okay because we just saw how to solve a min-cost circulation problem even if there are negative arcs. How do we solve it? Well, by saturating those negative arcs and turning it back into a min-cost flow problem without any negative arcs. Okay? So now we're really in pretty good shape, right? We have an algorithm that handles negative arcs, right? And its running time is m times the flow value. Now we have to be a little bit careful about what flow value means here, right? So in this reduction, what's going to determine the flow value? How much flow are you going to need to send? Yeah.
The total capacity over all negative arcs.
Exactly, right? In this reduction, right, the amount of flow that we have to spend is the total amount of excess, or the total amount of deficit. And where does that excess come from? That excess comes from saturating all of the negative cost arcs. So in this reduction, F is equal to the total capacity of the negative cost arcs. Okay. So, in the unit capacity case, right, then that total capacity is going to be less than or equal to m, right? That's the total capacity of all of the arcs. And so we're going to end up with sort of an m squared running time for the unit capacity case. Okay. Which is very nice, but we don't want to only solve problems with unit capacities. So how can we solve problems with arbitrary integer capacities? Yeah? Scaling, right? So now I'm doing new stuff, right? Again, this is what I think what I am assuming you got through on Wednesday. But let's talk about arbitrary capacities via scaling. So what's the general shape of the scaling approach going to be? Well, we're going to initially round down all of the capacities to 0, right? And then we're going to shift in 1 bit at a time, starting with the highest order bits, 1 bit at a time, 1 bit at a time of capacity, right? So shift in 1 bit at a time of the capacities. And then in each step, we're going to have to repair our min-cost flow. Right? And of course, initially, all the capacities are 0. So we know what the min-cost flow is, right? And we also don't have any negative arcs, since all the capacities are 0. We have no arcs at all. But what happens in a single scaling step? Right? We start with a min-cost flow of the previous phase. And then we shift the capacities. Now, what happens and what do we need to repair when we fix the capacities? So we double the capacities, and we sometimes add 1 to the capacities, right? Depending on whether we shift in a 0 or a 1. Okay. So how do we update our min-cost flow to reflect the new capacities? Well, one part of the update is very easy, right? We can double the flow values. That's the obvious thing to do first, because we've created twice as much capacity, we might as well use it, right? So we get something that's feasible, okay? But it might not be a min-cost flow. So what could cause the flow that we have created in this way to not be a min-cost flow? Yes?
There's some new augmenting path that we can send over to the one.
We need to be a little bit careful. We might have no augmenting paths and still not have a min-cost flow. How come? Yes? Right, if we're creating capacity, right? So again, when we double the flow values, we use up most of the new capacity, but we sometimes add 1. So we are sometimes creating capacity, and that means there might be some new edges in the graph that might create some negative cost cycles in the graph. Okay, so the new capacity might create some new negative cost edges. which could contribute to negative cost cycles, which could make our flow not min cost. It might also not be a max flow, right? We could create some capacity for additional augmenting paths, but even if we don't, we could have a problem, right? And in fact, let me simplify that away, and this was sloppy of me in my notes, but let's look at the min-cost circulation problem instead, so we don't need to worry about the extra capacity, and we're only worrying about those new negative costs, okay? Again, these transform between each other. If we can solve one, we can solve the other without any hard work, okay? So how do we deal with these new negative cost edges that got created? Well, I mean, basically, we need to find a min-cost circulation in the new graph. The question is, why is it easier to do that than to just solve the whole min-cost circulation problem at once? What can we say is special about the graph that we end up with through this process? Well, let's take advantage of what we have. Let's assume that with this previous min-cost circulation, that we also have a feasible price function on it that make all of the residual costs non-negative. Okay? So before the scaling step, no negative arcs in the network. Okay? Now we double some capacities. We sometimes add a unit of capacity. And now we might have some negative arcs. But what can we say about those negative arcs that we have? Yes?
The edge has capacity at most 1.
Yeah, I mean, it is an edge, right? We're creating negative arcs. But as you say, it has capacity at most 1. How come?
I would think that if it had capacity more than 1, it would have still been a negative arc in the previous.
Exactly, right? If we start with no negative arcs, now when we double the capacities and the flow values, we still have no negative arcs because we just doubled everything. So the only thing that can go wrong is when we add a unit of capacity to an edge, right? And our worry is we add a unit of capacity and that edge is now a negative cost edge, okay? But we know that it wasn't a negative cost edge before we added the unit of capacity, and that means it didn't exist until we added the unit of capacity. So the only negative arcs that we create are going to be arcs where we have created with capacity 1. Does that make sense to everybody? This is a critical idea. So, okay. So key observation is the moment of creation of new negative arcs is the final add 1 of the new bit. And the edge did not previously exist. Which meant it had capacity 0 before the add 1. Which means that the capacity of any negative arc is 1. So this is not something that's true in general min-cost flow. It's something that happens because we're taking a scaling step. Once we know that the capacity of every negative edge is 1, what does that tell us if we want to use a min-cost flow algorithm to solve it? Well, let's go back to the min-cost flow algorithm that we have, right? What can we say about this min cost flow calculation if we can rely on every negative arc having capacity 1. So we're going to use the unit algorithm, unit capacities algorithm, or the previous algorithm, which has an order mf log m running time. What can we say about f? Yes? Why is f less than or equal to m?
Because the only negative cost arcs. One.
Exactly. We are saturating negative cost arcs. Which all have capacity 1. And that means that at worst, we are creating at most m excess. Right? It doesn't matter what the capacity of the positive arcs are. Right? What determines the runtime of this algorithm is the amount of excess that's caused by the negative arcs, and they're all small. So we only create m excess, and that means that it takes us only m squared log m time to do a scaling phase. And that means that our overall runtime is order m squared log m log u. So we have a pretty nice running time for min cost flow with integer capacities via scaling. Any questions? There's an obvious question, now that I've given you a weakly polynomial algorithm. Is there a strongly polynomial algorithm, right? That's a very nice question. And it has a positive answer. There is, in fact, a strongly polynomial algorithm. Before I'm not going to teach you that, but I'll sort of point you at it. Notice that what we did here was we scaled on capacities, right? The costs can be real numbers because we didn't rely on, they don't show up in the running time of our algorithm. Okay? There is an alternative approach based on scaling costs, which allow your capacities to be real numbers as long as the costs are integers. Okay? And you will work that out next week in your homework. Okay? How to do capacity scaling. Okay. Now, before I get to the strongly polynomial algorithm, I want to show you one kind of other cool idea from min-cost flows, which is called complementary slackness. And this is an important idea that's also going to show up in our next unit on linear programming, but it's kind of nice to look at it in min-cost flows. So we're going back to thinking about the sort of capitalist model of min-cost flows, where the flow happens because merchants at the different vertices are setting prices for the commodity, and then shippers are choosing to deliver when they can make a local profit. Okay? We've already seen that all of these merchants think about reduced costs. In the residual graph, right? And so given that merchants are thinking about the reduced costs in your residual graph, what is a merchant going to do if they see a positive reduced cost on an edge? Remember, the reduced cost is the cost of buying at one end, shipping, and then selling at the other end. So what does a positive reduced cost tell that merchant to do? How much of this commodity should they purchase and ship if their goal is to maximize their profits? Yes? Right. Right. So if the reduced costs are positive, then every unit you send costs you something. So you're not going to do it, right? What if the reduced costs are negative? What should you do in that case? Yes. Send as much as you can. And what's going to determine how much you can send? What determines how much you can send on an edge? The capacity of the edge. You're just going to saturate that edge, right? What if it's 0? Well, if it's 0, then there's no profit or loss. You can do whatever you want, and it won't change your overall income, right? So a flow with these properties exhibits what is called complementary slackness. Okay, and the meaning of this complementary slackness is that the only time where the value of the flow is not pinned to one of its limits is when the cost is 0. So in a sense, the flow value is complementary to the costs. If the costs are non-zero, then the flow value is pinned on one end or the other. If the cost is 0, then the flow value can be arbitrary. Okay, and if you have a flow with complementary slackness, that flow is, by definition, optimal. Okay, the reason is that if you are saturating all of the negative cost arcs in the network, right? Remember that this can create residual costs, but they'll be positive because they're in the other direction, right? So if you have complementary slackness, then you have no negative cost arcs in your network, right? Which means that your flow is optimal because there are no negative cycles. Okay. Conversely, if you're optimal, you can create this feasible prices. These feasible prices cause you to have no negative value residual arcs. Okay. And that means that any negative cost arc is saturated, because that's what it means to not exist in the residual graph, right? The way an arc disappears from the residual graph is if it's saturated, right? So if your flow is optimal, you can use these feasible prices in order to get rid of all of your negative cost arcs. And that means that this price function, together with this flow that you've created, satisfies the complementary slackness conditions. Okay. And I mean, it's kind of a subtle difference, and it will be more visibly different when we look at general complementary slackness in linear programming. But it does let us understand more deeply what's going on with the with min-cost flow. All right. So in particular, if you are given a feasible price function, okay, how can you find an optimal min-cost flow in the network? Okay, or sorry, if you're given a price function which is feasible, that sort of corresponds. So again, what we've seen is that when you have a min-cost flow, there's kind of a corresponding feasible price function that proves the optimality of the min-cost flow, right? So suppose that somebody gives you that feasible price function that actually works with the min-cost flow, but they don't tell you what the min-cost flow is. Can you figure out what that min-cost flow should be? Like, does the feasible price function give you a hint that makes it easier to find the min-cost flow? Okay. Well, let's look at what that feasible price function does, right? It causes various edges to change price, right? To be positive, negative, or zero cost. Okay. So if I look at this feasible price function, and now I look and see, okay, under the feasible price function, this edge is negative cost. What does that tell me about the min-cost flow on that edge? Yeah? Right. If the minimum cost flow is negative, if the feasible price function makes an edge have negative cost, then the min-cost flow must saturate that edge, since otherwise it would be in the residual graph and it would have a negative cost. What if the feasible price function makes an edge cost positive? What happens to that edge in the optimum min-cost flow? Well, that's as we said over here. If the cost is positive, you don't use it, right? So any edge with a positive cost under the feasible price function goes unused. It's empty. So from the feasible price function, we know what should happen to all the positive cost arcs, which is that actually we can delete them. They're not used in the min-cost flow. We also know what happens with all the negative cost arcs. We know they have to be saturated. Okay, let's do that. Let's saturate all the negative cost arcs. What effect does that have? We just did that in the scaling algorithm, right? When you saturate the negative cost arcs, it creates excesses and deficits in the network, right? But we know there's supposed to be a min-cost flow solution. It doesn't have any excesses and deficits in it. So how are we going to send those excesses to the deficits in order to eliminate them from the network? What do we have left to use? Right, I've already told you that we can't use the positive arcs and that we're saturating the negative ones, so how do we send the excess back? Yeah? Only the zero cost arcs are unknown or have any flexibility, right? So once we know this, we have to send the excesses to the deficits on the zero cost arcs. Now, if you're sending the excess to the deficits on the zero cost arcs, what kind of algorithm do you need in order to solve the problem? If all the costs are zero, do you need to solve a min-cost flow problem? Yeah? You don't need to worry about costs anymore. You just use regular max flow. Right? whatever flow you use is going to have cost 0, which means that it's going to be a minimum cost way to send the excesses to the deficits. Okay? So there's this really fun duality, another concept we'll be looking at next week, right? We've already seen that if somebody gives you the min-cost flow, it's easy to compute the price function, because all you have to do is compute shortest paths. What we see here is that if somebody gives you the price function, then it's really easy to compute the min-cost flow, because you can use any old max flow algorithm for it. Make sense? So in a really deep way, what this tells us is that min-cost flow is equal to max flow plus shortest paths. Right? If you subtract the max flow part from min-cost flow, then you're left with the shortest path problem. If you subtract the shortest path problem from min-cost flow, then you're left with a plain old max flow problem. So it was always there, it was just disguised, and we needed to introduce this whole concept of feasible price functions in order to prove that this relationship between shortest paths, max flow, and min-cost flow. Okay? And so this complementary slackness idea is actually really important in practice in the design of min-cost flow algorithms. There's lots of min-cost flow algorithms. I've only shown you a couple. And some of them use complementary slackness to prove correctness of what they're doing. Others use complementary slackness to guide the solution algorithm itself. And so I'm going to mention briefly the problem of computing a strongly polynomial min-cost flow. This was open for a long time. It was solved in 1985 by Eva Tardos, who's one of the giants in combinatorial optimization, professor at Cornell. The technique that she introduced was was a cycle canceling technique, but you don't cancel any old negative cost cycle. Instead, you look for the minimum mean cost cycle. What's the mean cost of the cycle? It's equal to the cost divided by the number of edges. Okay. And there's some sense to this, like some intuitive sense to it, which is, if you have if it takes you a really long cycle to get negative cost, then in a sense, each edge is only contributing a little bit of negative cost, right? If it's a very short cycle, then each edge is really more negative than it is in a long cycle of the same value. So this sort of suggests looking at minimum mean cost cycles. And we've already seen cycle canceling, like Klein's algorithm for cycle canceling. And you'll be thinking about ideas, not mean cost cycle, but you'll be thinking about cycle canceling when you do the cost scaling, right? But the trick with minimum mean cost cycles, how do you, sorry, what do I want to say here? This is a plausible idea that leads to other useful sort of scaling type algorithms, right? But you have the same problem or the same concern that if you have really big numbers, you may need to cancel many, many cycles before you're able to get down to the last bits of the number. So the insight that Tardos had was that if you have really large values on your edges, then future scaling phases can't change them enough to make you change your mind about what you're doing with the edge. So she uses this idea, which she calls epsilon optimality, which is to basically use the complementary slackness ideas to give you a measure of how close you are to the optimum. And once you know that you're pretty close to the optimum, it tells you that edges of very negative reduced cost must be saturated. Because if they had even a little bit of flow, if they had even a little bit of residual capacity, they would contribute to a cycle of negative cost. All right, so basically, once you're very close to optimum, there can't be any very negative cycles. There can only be slightly negative cycles. And so any edge that's very negative can't be in one of your cycles. And so you can saturate that edge and forget about it. Okay. And the benefit is that you don't have to keep worrying about more and more bits that may come in and force you to re-examine that edge. You just know that forever that edge is going to be saturated. And since you can saturate edges of very negative cost, in a sense, your scaling algorithm doesn't need to be thinking about arbitrarily big numbers, right? The numbers that matter in the scaling algorithm are only polynomial size numbers. Costs of polynomial size or polynomial value. And if the costs are themselves polynomial in M and N, this means that the scaling algorithm is strongly polynomial. Because you're not dealing with arbitrarily large numbers. Okay? So if you want to go find out about how to get a strongly polynomial min-cost flow algorithm, you can read about this work from Tardosh. Okay? In practice, just to finish up the story, the best running times, the best strongly polynomial running times are around m squared, similar to the bounds that we already found with scaling. But if you use a technique called double scaling, where you scale on cost and capacities, you can improve the running time to mn log c times, oddly enough, log u. So if you're willing to have a dependence on the values, then you can get your min-cost flow algorithms to have the same kind of mn time bounds as we derived for regular max flow. Okay. And so far as I know, I mean, I just shared an article about the linear time max flow stuff that appeared in Quanta. You can read about that for a little more information. I don't think that all of these breakthroughs on max flow have led to solutions for min-cost flow. If anybody knows otherwise, you should tell me. But to my knowledge, the breakthroughs right now are just for uncosted max flow. And introducing costs sends us back to these combinatorial algorithms for the problems. Okay. All right, that's the end of the story for min-cost flow. And the next thing we're going to do is transition to a much more general problem called linear programming, of which everything we've looked at, shortest paths, max flow, and min-cost flow, are all special cases. And we'll spend the next week on that, but let's gear up for it with a short break. Yeah. Oh, wait, sorry. Is it that they compute a min-cost flow of the original network, or that they compute, like, I know that they use costs along the way to finding the original flow, to solving the original flow problem, but do they actually, if you pose a min-cost flow problem, do they actually solve that as well? Okay, cool. M to the 1 plus epsilon. Yeah, okay. I'll clarify to the group. Thank you. All right, so somebody peeked at the article and told me that the article says that the new techniques solve the min-cost flow problem as well. I'm not sure how they incorporate costs into what they're already doing. As I understand, what the techniques that I understand there sort of rely on creating an artificial cost in order to sort of steer the algorithm, and it kind of collides with the costs that you actually want to use, but they seem to have overcome that. Also, just a reminder for people who came in late, there's no class on Monday, so don't come. I mean, it'll probably be nice and quiet if you want to rest or something, but there won't be any lecture. So, linear programming. So, yes? Yes. Yes. This is a very good point. So I claim that in this graph that where we've created excesses and deficits, there is guaranteed to be a flow that sends all the excess back to the deficits. Anybody see why? How did I create these excesses and deficits? Yeah?
You just push it back on the same edge.
Yeah, I created these excesses and deficits by pushing flow along negative cost arcs, right? But if I push flow along an arc, it creates a residual arc in the opposite direction. So one way to send the flow back is to just use the residual arcs I've just created. But that is not the cheapest way to send the flow back, or might not be the cheapest way to send the flow back, right? So that's why we use a min-cost flow algorithm to send the flow back. And so if you think about it, that original pushing, right, combined with the min-cost flow that I compute, together those form a min-cost circulation, which is what I need in order to destroy all of those negative arcs. Okay? Good question. Thank you for holding it for class, so everybody else could hear it too. All right, so linear programming. linear programming is definitely one of the sort of giant achievements of combinatorial optimization in the 20th century. It's used everywhere. And it's an incredibly powerful sledgehammer for solving a really wide variety of problems. And I'll be showing you a bunch of examples of things that you can solve with linear programming. In particular, you can solve min-cost flow just by feeding it into a linear programming solver. Because what is min-cost flow, right? This is trying to minimize the sum of some edge costs times some flow values with constraints that the flow values need to be bounded by 0 and some capacity bounds, and also with various balance constraints, right? So this is min-cost circulation that I've put in here, right? I'm just going to say balance. Everything has to be balanced everywhere, right? So what do we have here? We have a linear objective function. Sorry, we have variables. We have a linear objective function. And we have a collection of linear inequality and equality constraints. And that completely defines the min-cost flow problem, right? So the linear programming problem is the general version of this. Take any collection of variables with an arbitrary linear objective function over those variables and find the optimum solution, be it a minimum or a maximum, constrained by a bunch of linear inequalities and equalities in those variables. Okay? So everybody understands the problem? Okay. So all of the combinatorial optimization problems that we've looked at so far can be formulated as linear programming problems. The shortest paths is actually a little trickier than Maxflow to think about how you would formulate it as a linear programming problem. It's a nice little exercise, but it can be done. And certainly Maxflow and min-cost flow. Now, linear programming, this problem was defined during World War II. I don't think it was explicitly named before World War II, but in World War II, the war effort involved a lot of logistics problems, right? How much stuff should you ship from here to there? How much should you spend on these things versus those things? How should you how should you combine ingredients so that the soldiers have balanced diets, right? Sort of a wide range of problems that needed to be solved in World War II. And people realized that they could all be formulated as linear programming problems. And a guy named Danzig developed the first algorithm for linear programming called the simplex algorithm. And this was in sort of the early days. This was when people weren't sure you could actually solve linear programs at all. And so he came up with the first algorithm that actually gave you the optimum solution. But you notice he was doing this during World War II. And so this was before the invention of theoretical computer science, right? And so he didn't have anything much to say about runtime, right, or polynomial or anything like that. His key contribution was that this algorithm is correct, and it eventually terminates with the optimum answer. Okay? And again, in practice, it often works really, really well. And again, it was sort of revolutionary before we understood it theoretically. It was already incredibly valuable in practice. But when the computer scientists came along, they asked the obvious questions, right? They wanted to know whether linear programming was in NP, right? You've all seen, or I hope you've all seen NP completeness, and this sort of large class of problems that can be solved at least if somebody tells you what the answer is. You can check that the answer is correct, right? So people weren't sure if linear programming was in NP, whether it was in co-NP. And then, of course, there was this giant question of whether there was a polynomial time algorithm for it. Okay. And so it turns out, if you look at it, that the simplex algorithm actually does prove that linear programming is in NP, which, again, is not obvious. It's a nice thing to know. The question of whether linear programming could be solved in polynomial time actually stayed open until the 70s. With the invention of something called the ellipsoid algorithm. It was the first polynomial time algorithm. It's only weakly polynomial. But the ellipsoid algorithm is incredibly cool, and I'll give you a lecture on it. It can do things that are unbelievable, but it is a theoretical algorithm. In the 80s, a class of techniques called interior point were developed, which are weakly polynomial and do lead to practical algorithms as well. Okay. And now every large optimization, any company that's doing substantial optimization, I can guarantee you that they have a linear programming solver somewhere inside that company to do, flight scheduling for airlines and transportation logistics and everything like that. So I'm going to teach you, I'm going to sort of take you through some of this history with details. We're going to start by formulating linear programs, and we're going to go through a sort of natural series of questions. We're going to ask sorry, where's my list of interesting questions? Yeah. We're going to ask, what does the answer look like? How do we know if we can write down the answer to a linear program? Maybe it involves real numbers that require infinite precision. Okay. So can it be represented in finite space or efficiently? Okay, once we know we can write down the answer, we're going to ask about feasibility. So suppose that we don't worry about the objective function. We just say, here's a collection of linear inequalities. Can they all be satisfied at once? Okay. If you think about it, it's pretty easy to verify that there exists a solution to a feasibility problem. Is it possible to verify that there is no solution? Okay. How do you convince somebody to stop working on a linear programming problem? Okay. Then we'll start asking about optimality. Okay. Can we verify a given solution is optimal? If it's not, can we improve it from what it is to something better? And if we think about these improvements, how fast can they reach the optimum? Okay. So these are all similar to the questions that we asked about min-cost flow, but we're now working in a much more general setting. Okay. So let me give the sort of formulation of linear programs. Now let's just use the new board. So as I said, a linear program is any old objective function and any collection of linear equalities and inequalities over the variables. But it turns out that every linear programming problem can be transformed into what is known as canonical form, which is to write it as a maximization problem where x is your variables and c is a bunch of coefficients. And the only constraints you have are upper bounds. So here A is a matrix. B and C are vectors. Okay, so this is a generalization of the standard AX equals B notation, right, which says that the left side should be coordinate-wise equal to the right-hand side. Instead, we're saying that each coordinate on the left side should be upper bounded by the value on the right side. Okay, so you can think of this as just a collection of linear inequalities. Everybody understand the formulation? All right, so it's nice to have this formulation because we can use it to sort of state theorems. If we want to state theorems about linear programs, we can just state them about the canonical form linear program and know that they apply to all linear programs. Notice that in this representation, C is a row vector, and I should probably be writing C transpose, but I always forget my transposes, so I'm just going to leave them all off. So that there's no inconsistency, and leave it up to you to recognize when we have row vectors and when we have column vectors. So in this formulation, the rows are denoted by AI, and they are what are called the constraints of the linear program, right? So we have a collection of constraints, AI x less than or equal to bi. C is known as the objective function, even though it's just a vector. The function is the dot product. Okay. And the claim is that we can transform any linear program into this canonical form. So how do we do that? Well, a linear program can be either a minimization or a maximization problem. How do we transform a min problem into a canonical form maximization problem? Yeah? Exactly. We just negate the maximum of the negated objective function. Okay? So that's easy. Now again, a linear program can have arbitrary constraints. So we might have a constraint of the form, AIX plus, sorry, let me be careful of my letters. QIX plus RI is less than or equal to SIX plus TI. So that's an arbitrary linear constraint which does not look like the constraints of the canonical form. What should we do? Yeah? Yeah, we just move things around, right? So we just say that QI minus SI times x is less than or equal to ti minus ri, and so that's fine. What if we have some greater than or equals constraints, right? What do we do with AIX greater than or equal to BI? Yeah? Yeah, we just say minus AIX is less than or equal to minus BI. That's fine too. What do we do with equality constraints? Yeah? Exactly. We just make two inequalities. And of course, we'll immediately transform one of them using the previous rule. Okay. So that is the canonical form. Right? We can using these simple rules, we can transform any linear programming problem until it has this formulation. Okay? So that's great, except that the optimization people couldn't agree. And so they decided to also define something called standard form. Standard, of course, is a synonym for canonical. But standard form is different from canonical form. So standard form writes any linear program in the form of a minimization problem where the constraints are all equality constraints, and the inequalities are all expressed by requiring the variables to be non-negative. Okay. And I mean, it's a little bit surprising that you can turn every linear program into this form. Like, where did all the inequalities go, right? How did we get rid of them and just have non-negative variables? And for this, you use a trick known as the introduction of slack variables. So if you have a constraint of the form AIX less than or equal to BI, right? We've already done all the transformations into canonical form, so we only need to understand how to transform canonical form into standard form, right? So if we have a constraint of the form AIX less than or equal to BI, what we do is we introduce a new variable called a slack variable, and we write AIX plus SI should be equal to BI, and SI should be greater than or equal to 0. Okay. So SI represents the amount of slack in the inequality, and we're saying that if this inequality is satisfied, it means that there is a non-negative slack. Okay. Okay, so this means that we get rid of all of the inequality constraints and turn them into equality constraints along with some non-negative slack variables. But this still isn't canonical form because some of our variables might still not be constrained to be greater than or equal to 0, right? If I start with an arbitrary linear programming problem, well, there might not be rules for some of the xi's. Maybe some of the x's are allowed to be positive or negative, right? So what do I do if xi is unrestricted in sign? How can I turn my linear program into standard form? Well, again, a simple trick once you think of it, I write xi as the difference of two variables, xi positive minus xi negative. Okay. So I introduced two brand new variables, and essentially xi plus represents xi when xi is supposed to be positive, right? In that case, you can set xi minus to be 0 and xi plus to be xi. If, on the other hand, xi is supposed to be negative, then you set xi plus to be 0, and you set xi to be the absolute value. You set xi minus to be the absolute value, right? And now you can constrain both xi plus and xi minus to be greater than or equal to 0, and it's fine, right? These constraints, since you're just subtracting them, these constraints don't actually restrict anything, but they do achieve our goal of having every variable be constrained to be non-negative. Does that make sense? Yeah? OK, so now we have a canonical form and a standard form. I will say that the canonical form tends to be sort of more elegant for proving theorems, and the standard form tends to be more important for implementing linear programming algorithms in practice. And there's actually a really cool connection between them that we will see next week. Okay? But for now, you can just think of them as two distinct representations of linear programs. So we only have 5 minutes left. I'm not going to prove anything more complicated, but I'm going to tell you about our plan. The way we're going to approach this is that first we're going to think about linear equalities. And we're going to ask the same kinds of questions about just systems of linear equalities, right? AX equals B. We're going to ask, what does the solution to a system of linear equalities look like? We're going to ask, can you verify that a solution is correct? The answer to that is pretty obvious. We're also going to ask if you can easily verify that there is no solution to a system of linear equalities. And we'll also talk briefly about how you actually can find that solution. So just to start with a sort of baby case is where A is a square matrix, and the solution is unique. So, this is like the kind of problem that you got in high school, or maybe elementary school, given that you're at MIT. How do you go about solving AX equals B? How do you know when there is a solution to AX equals B, or when there might not be a solution to AX equals B? What do you remember from primary school? Yeah? Right, so you can solve it by Gaussian elimination. Okay. Well, and this did work in high school or nursery school or whatever. But are we sure it works? So, now that we understand computers and we know about fixed precision, right? That you can only fit a certain number of bits into a machine word, right? Is this always going to give us an answer that can actually be represented in the computer? I mean, what if Gaussian elimination? What if the end result is real numbers, right? Or even if they're not real, what if the end result requires so many bits of precision that you can't fit them into your computer? Right? So even with the sort of simple linear system of equations, we have to think before we get to actually solving it, we need to ask about how is the solution represented, or the size of the solution. And so this is something that we've been ignoring until now, right? Because all we were ever doing was adding numbers, and that seemed relatively safe, okay? But for Gaussian elimination, you need to add, multiply, subtract, and divide at various times. What might that do to the numbers, right? So we'll talk about that later on. Let me just mention that when it comes to a square matrix, as you know, the following are all equivalent. In terms of solving AX equals B, in order to do that, you generally want A to be invertible. This is the same as having the transpose of A be invertible. This is true if and only if the determinant of A is not 0, which only happens if A has linearly independent rows. It also only happens if and only if A has linearly independent columns. And if any of these are all equivalent to AX equals B having a solution for every B, having a unique solution for each B. And that's actually equivalent to AX equals B having a unique solution only for one particular B. So basically, it's all very nice or it's all terrible. It doesn't depend on the particular value of B that you're working with. Okay. So next time we will talk about this issue of representing the solution and making sure that we can fit it in polynomial space. And then we will talk about these linear systems. Again, assuming you can represent it in polynomial space, how do you prove to somebody that there is a solution to AX equals B? It's pretty easy, right? How do you give somebody an easy to check proof that there is a solution to AX equals B? Yeah? Give them X, right? Here's X, just check that AX equals B, problem solved. But there's a much more interesting question. How do you make an equally easy proof that there is no solution, right? So that will be sort of our first theoretical accomplishment on Wednesday. And once we do that, we'll have sort of a full understanding of linear systems, and then we'll move on to linear equalities for the rest of the week. So enjoy your vacation, and I will see you on Wednesday.